Okay, I'm just gonna go ahead and get started. So this is the first under review being hosted for Kim and Mahapatra's 312. My name is Caitlin. I'll be doing them for this semester. So, gonna go ahead and get into it. So this week's overview is gonna talk about hardware organization, Amdahl's law, code representation levels, compilation, as well as just a few things to help understand question 4, like bitwise operators and reading binary. So first off, just gonna go over the stages of compilation. So this is basically how you're getting from your code to an executable. There's a bunch of little silly stages in between. So first off is the preprocessor stage. This is the first stage that your code is going to go through. So you write something in C, you use this command here, and that's preprocessing. So basically, it is going to just go through your code, remove all the comments so that it doesn't have to read those in further stages. It'll expand things. So if you have a header, say you include math, like C math or something like that, it's gonna go ahead and expand that and find that function and will expand macros. So if you have a function, say add AB, it's gonna turn that into what it should actually be doing. And it's gonna go from a C.C to a .I file. Next up is the compiler, and the compiler stage to get past the stage, you'll run this command. You start with your .I file that you got from the preprocessor, and it'll turn that high-level program, so everything that you previously had minus your comments with everything expanded, and it'll turn that into assembly language. So this is just a quick, easy example of how assembly can work. So if you write in C, int x equals 10, in assembly that's going to end up being move L 10 EAX. So it's essentially just moving the value 10 into the register EAX, which you can think of just as like a little box, which we'll talk about registers later when we get into hardware organization. And that's going to turn that .I file into a .s file. And then your .s file will go into the assembly stage, or assembler stage, where it's going to turn that assembly level language program into machine code or object code. Now this could be binary, hexadecimal, or it could even be stuff that you can't read. And it's just the computer changing that language, that assembly language, into something that it can work with further. And that'll change your file from a .s that you got from here to a .o. Now you run this command and you are then making it go through the linking stage where it creates that executable for you. So this is going to resolve references between files. So if there are, say for example, everyone remembers the very first assignment from CSCE 120, 121, I think it's grade calculator, but you have a file that is grade calculator that has your main in it, that has where you're asking these are for input, providing an output, and then there's also another file that has all of your functions that will calculate that grade. So what it's doing is it's making sure that those two are linked together so that they can work together. And then this should say run. Ignore that not saying run. After that, you can then run the executable file and you will be able to see the output results from that C code you wrote. Now, we usually skip all of these stages and just combine them into one when we run something just like gcc filename.c-o and then give it a name. But this is it all broken up. Cool. So next up, we're going to talk about hardware. So I'm not saying to memorize this whole thing. That's a lot. Memorizing it is not going to get you anywhere. But it is going to be helpful to understand how things connect, especially as we get further on into the course. So this big box here is the CPU, and it holds all of your register files. So that thing I was talking about earlier that stores data that you can access in assembly, register files, your PC, your program counter, the ALU, the interface that then goes to the I/O bridge. Your main memory is connected through the I/O bridge. And then this is the I/O bus, which is basically just big, long wire. You could think of it almost like a wire that you can then connect everything else to. So your display, USB controllers, like if your camera is set up to it or your mic, that's how it's going to connect with the computer CPU, all of your disk stuff, etc. Okay, so here's just a few more. These are the parts that you really need to understand what they are specifically to help you understand how it functions. So the CPU is obviously the central processing unit. It's where everything that is going to be actually processing your program is held. The ALU is the arithmetic logic unit. It does all of the math. So if you have, say, you want to do 2 plus 2, the ALU is going to do that math for you. It's going to compute the new data and where it should go. The register file thing I talked about earlier is where you will be storing that data. Registers are labeled in x86, which is what you'll most likely be working with EAX, EBX, ECX, all the way down to ESP, which is your stack pointer, EBP. And then you can also have like, once you run out of those, there's also ones named like R18, R whatever. And those are just places to store data. The PC is the program counter, not the personal, it's not a PC like you would work with, like your personal computer, or like if you're going to Best Buy and you ask for a PC. The program counter instead keeps track of what level of instructions you're on. The USB is the universal serial bus, so that is just a bus that lets data travel either two ways in a bidirectional or unidirectional one way. Your main memory is going to be where everything is stored in the form of like DRAM chips, and it'll hold all of the data and changes. So you can see here. So this is data that is currently being worked on by the CPU. That's the register file. That's the kind of data that register file stores, is stuff that is in use. Main memory is stuff that you may have to go grab, if that makes sense. The processor will interpret the instructions from main memory and will be just executing those instructions repeatedly. So the PC, you can kind of think of it as like a big box where the PC is pointing to something. This might be more helpful to draw. I'll draw it. So you have this instructions, right? So the PC is currently pointing to this one. So the processor will run all that stuff. This arrow will get moved to here. It will then I'll run all that. The program counter will move again because it's already run those, and it'll continue on. The ISA is the instruction set architecture that holds, basically it has all of the I/O devices, the instructions, etc., that will make a program work. And then abstraction is what we just call the interface, which in this case, the interface is the ISA that is between hardware and low-level software that helps deal with how complex things are. It's just kind of a buffer layer that helps everything work together. Okay. Next up, just going to talk about memory a bit more. So you usually see this diagram in kind of a pyramid shape where registers are on the top and remote storage is on the bottom. So registers, talked about it a ton already. Those are the things labeled with the 3 letters, so EAX, etc., that hold data temporarily. Then we have L1 cache, which is SRAM. L2 cache, main memory, which is here. The local disks and remote storage. Remote storage is like cloud storage, where local disk is something physical that you have stored on your, like connected to your rig. So as we go up, things are going to get smaller, faster, and more expensive. So L1 cache is going to be more costly than main memory, but it's also going to be faster and smaller, so you can have more of it. And as you go down, obviously it goes in reverse, larger, slower, and less costly. Okay, next up is Amdahl's law. So this is the equation that y'all learned in class. So this is for T new, speed up, obviously a lot of letters, symbols. It's easier just to think of it as you're almost having like a fraction where you are like in chemistry where you're having like, I have this many of this much. How many do I have of this much? Like the little comparison thing. It's kind of like that, basically. And it's much easier to work with if you have an example. So I have an example. Um, so say your new GPU is 20 times faster than your original. So you can already know that that's new versus old. Assuming that you do computation 30% of the time, what is the overall speed up gained by the enhancement? So your K, your improvement factor, is going to be 20. Wow. And your fraction of time that will be improved is this 30% that you're doing computation. If you are doing something else besides working on problems, getting things computed, for example, this one is waiting for memory access, that is not improvement of time working. So that's how you can help differentiate between which number goes there. It's the time that it's actually spent working. And then you can just plug it into the equation. So see, I used this speed up equation. Instead of working with this one, because I don't want to calculate T new, because we don't have T old, I just used the latter half, which is this one. Oh, I cannot write. Wow. 1 over 1 minus alpha plus alpha over k. So I just plugged it all in there. And then you get the speed up to be about 1.3986, which is just an improvement factor of, I think like 30 or 40%, basically. So yeah. Next, we're gonna talk about bitwise operators. So these are gonna be more helpful for the lab, especially lab 1, and just understanding in general in the future. So we'll do this one first because this one's pretty easy. So this is a bitwise OR operator. Usually if you are doing an OR operator in your program, it's gonna have 2 of these, right? So that is the whole OR. This is just bitwise OR, so it's one symbol. And so it would be like, if you were writing it out, it'd be 1 or 6, like this. So technically I would go in between here, but I wanted to space it out because these are the results. So, but that's how you interpret it. So 1 or 6 in this case is equal to 7 because what you do is you compare each bit to each other. So you're comparing each bit of the first number to each bit of the second number, the same placing. So this is the 2 to the 0th bit. So we're going to compare those two. With an OR, you need one or the other or both. So that's why we get 1 here, a 1 here, and a 1 here, but zeros everywhere else. And then this number is 7. So this is a more complicated OR example. So once again, you're just going to be comparing each bit. So this first number is equal to 67 in decimal. So 67 bitwise or 21. These are both 1s, so you get a 1. There's a 1 here, 1 here, zeros, 1 here, zeros, 1, zeros. And that is equal to decimal 87. So this is a bitwise and, same thing as the OR. Usually you see it as a double ampersand. But in this case, because it's bitwise, there's just one of them, so it would be written in your program as 22 and 5. So it's the same thing as the OR, where you're going to break them up into each place. But this one, it has to be both. So same thing as an AND, like a regular AND operator. So it says one of them 0, 1, 0, both 1, 0, 0, 0, 0, 0. So 22 and 5 is equal to 4. Now, how can you use this to help with your lab? So say you were working with 3 bits and your input was, this is a bad place to do this. Ignore these. Those don't exist. Um, so you're working with 3 bits, your input is 2. But you don't know that. You don't know that your input is 2. So you want to make sure that that input has a 2 in it. So what you can do is you can use an AND with a 2, because, you don't know what this one is. And if your result is equal to a 2, you know that that input was also 2. Okay. So if that was confusing, it's probably because you don't know how to read binary. So this is a breakdown of how binary is read. So in this first lab, you only need to have up to 8 bits, and they start in the far right placement. So 2 to the 0th, 2 to the first, 2 to the second, all the way up. And as you get even more going to the left, then that 7 is going to be pretty, like it's gonna keep increasing. So this is 2 to the n. Um, so yeah. So for this purpose, I just put some random 1s and 0s in there. But how you add everything up is you go 1, I have 1 of 2 to the 0th, which 2 to the 0th is 1. I have 0 of 2 to the first, 2. 1 of 2 to the second, which is 4. 8, 16, 32, 64. This will be 128. So now we know we have 1, 1, 0, 2s, 1, 4, 1, 8, 0, 16s, 132, 164, and 0, 128. And we add all that up to get 109. So this 8-bit is an 8-bit representation of the decimal number 109. And that's how you read any binary number. You always start at the 2 to the 0th and you read upwards, incrementing with each placement. Okay. So that is all I had for today, based on lecture material and lab material. So if you have any questions, I can answer them now. Otherwise, I appreciate you coming. Today was kind of short, but there hasn't been a ton of material yet. So yeah, you're welcome. Thank you for coming.